Welcome to today's webinar. The topic today is consideration of torsional warping in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, technical content of the website, German and English webinars, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague, Dr. Jonas Bien, will be the presenter. He's responsible for customer support and for the product development of the add-ons, steel design, structure, stability, torsional warping, and so on. Okay. Then before he starts, I say something how you can ask questions. At first, I switch off my camera that you can see the full screen. You can press that button with the question mark, enter your question in that field, then press send, and I will receive your question, and then I will answer the question. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Jonas. Jonas, it's your turn.
Andreas, thanks a lot for your introduction. A warm welcome also from my side. Nice to have you here in the webinar. Today, I want to focus on torsion and warping torsion in particular. This can be considered in RSTAB 9 and RFEM 6 on the global structural level by using our add-on warping torsion. I want to start with a short theory section to explain the basics of torsional warping. It's quite a complex topic, which means that, of course, we can only scratch the surface within this webinar. The aim here is to familiarize users that have not yet looked into this topic with the concept of warping torsion. I want to enable all of you to assess if warping torsion may be relevant in a specific situation or not. So that's our goal for today. Moreover, I want to explain some peculiarities that need to be considered when setting up a 7 degrees of freedom calculation in RFEM 6 or RSTAB 9. Although the assumptions and required settings are very well explained in our online manual, there are some questions that come up very frequently, and I want to cover them here to clarify them once and for all. Last but not least, I want to demonstrate the influence of warping torsion on selected but very typical structures or substructures. During the preparation of this webinar, I realized that it might be a bit tiring to have 30 minutes of pure theory, so I will try to mix up all these ingredients that I mention here on the content slide, rather than going through them from top to bottom. I will focus mainly on simple and very clear examples to highlight the influence of specific parameters on the torsional load-bearing behavior that we can investigate in RFEM. For this introductory slide, I put a snapshot of a twisted eye section in the lower right corner right here. This is not by coincidence. So in fact, most steel profiles are optimized for bending rather than transferring torsional load and are particularly affected by warping torsion. So we will mainly focus today on steel profiles and on steel sections. I will maybe lose some words also on solid sections, but this will not be the focus of this webinar. Although it is good practice, of course, to avoid direct torsional loading by design for such sections, it is not always possible to do so. And hopefully, after this webinar, we are a bit less scared to deal with such cases if we encounter them. So let's start with some fundamentals. In the general case, a beam that is loaded in torsion will experience twisting, shown on the right side if we look from the front on this distorted beam, and warping. So if we look from the side, we see the warping deformation. This combined reaction to a torsional load is described as mixed torsion. In a conventional spatial beam analysis, only 6 degrees of freedom per node, so on each member end, are considered in the analysis. These 6 DOFs are made of 3 displacement degrees of freedoms and 3 rotations. Warping is usually not part of the solution, and this is not special for our usual simulation, but also is in fact the standard or convention in most software solutions. In RFEM and RSTAB, we can, however, very easily activate the 7th degree of freedom by just activating the torsional warping add-on. You may now ask why warping is not considered by default when the general case for beams under torsional loading is mixed torsion, so it also needs to consider warping. In fact, there are many practical cases where we can neglect it without making a huge error, and we will talk about that today. But before we join into this, we want to discuss the main features of the two load-bearing mechanisms that are activated and shown here on the slide, so twisting and warping. So let's go to the next slide. In a simulation with 6 degrees of freedom, only the sans venant or primary torsion is considered on a beam element. The beam twists, as shown here on the upper right side, which means that the section rotation along the beam varies. So we have a rotation of the start and of the end of the beam, and they do not align with each other. This twisting goes along with the development of primary shear stresses in the section. For thin-walled open sections, shown here on the lower left corner, those shear stresses act in opposite directions on opposite faces of the section parts. I try to make this a bit clearer when drawing the shear flow here in this little section. Each section part, so the flanges and the web in this example here, take their own little portion of the torsion load. With reference to the shear center of the section, however, the stresses largely cancel each other out. For closed sections, here one example on the right side, rectangular hollow section, the shear stresses are almost constant over the thickness, which means that the shear resultant of a section part has a large lever arm on the shear center. Also, the shear stresses are oriented in the same rotational direction, and as a result, the primary torsional shear stresses are usually much smaller in closed sections compared to open sections when applying a similar torsional load. The integral of the primary shear stresses is equal to the primary torsional moment, mt pri. With the 7th degree of freedom, the section warping is activated. Warping is defined as a non-uniform axial deformation of the section as illustrated in the upper right corner. So if we focus on the right side of this beam, we can see that two edges deform in the plane of this member, whereas the other two edges deform in the opposite direction. For thin-walled open section, this axial deformation is linear over each section part. As we can see here, the flanges show a linear deformation along the beam axis. In case warping of the section is somehow constrained, axial stresses affine to the restrained deformation will occur. Similar to axial bending stresses, the axial warping stresses needs to be balanced by shear stresses. Those shear stresses that are required for equilibrium are called secondary torsional shear stresses. When we examine the stress distribution for axial warping stresses here on the lower right corner and the corresponding shear stresses here for the thin-walled analysis solution, we directly see the analogy between the axial bending stresses and shear stresses due to shear forces. So it's very obvious. This looks a lot like the shear stresses that are coming from shear force acting in the web and corresponding to the elastic bending stress distribution for bending around the strong axis in such a profile here. The integral of the axial warping stresses are called the warping moment or bi-moment, whereas the integral of the secondary shear stresses forms the secondary torsional moment. Similar to the stresses, there is a clear relationship between those two internal forces. The warping moment is equal to the integral of the secondary torsional moment along the beam, which is again in analogy to the bending theory. The figures that are shown here are, for illustration purposes, are taken directly from RFEM, and I want to show you where you can find those to check the stress distribution for any profile that you are working with within the program. So I just have here an empty file. I just generated some sections with different properties with regards to bending, warping, but we will come to that later. I just want to show you for now where you can find all those handy stress distribution plots. Therefore, you just go to the section dialog, and then underneath this figure here, you can see that there are a lot of functions built into RFEM where you can assess something like unit stress distribution for finite element analysis. That's where the section is discretized in 2D elements. You can check the mesh here by clicking on this little mesh symbol. And here you get, for example, the unit stress distribution over the profile for the primary torsional moment. Or you can check the same information for the thin wall analysis results, where we assume that the stresses are constant over the thickness and that the stresses are not zero at the edges. So this is also quite nice. And we have access to several other functions, such as the warping, torsional warping function, and so on, that is affine to the warping deformation and the actual warping stresses if warping is restrained. Okay, but for now, before we start anything crazy here, let's go back to the presentation, because we have to clarify one or two more things before we go to the first example. All right. So what have we here? This is basically, so we were talking about the primary torsional moment and the secondary torsional moment. And in the introduction, I said that the general case has both of those parts. So has a part that comes from primary torsion and one that comes from secondary torsion. And the overall torsional moment makes up of those two components. However, quickly the question arises how the relative magnitudes of the primary and the secondary torsion can be determined. So how are they distributed, both parts? A quick assessment of this torsional differential equation helps in this respect, because we can directly see that the primary torsional moment is related to the torsional stiffness, while the secondary torsional moment is connected with the warping stiffness here. Both parameters are constants for a given section and material, so the relative magnitudes of primary and secondary torsion should be largely dependent on the section choice. And we can also go one step further, so it's very common to simplify this torsional differential equation by dividing by the warping stiffness, and then we get this factor that stands here in the square root. And this part of the equation is then called the decay factor. And this decay factor has some meaning. The greater the decay factor, the faster the secondary torsional moment is reduced in the vicinity of a warping restraint. We will try to check if this is true or if it holds in the RFEM calculation within the first practical example later. The product of this decay factor here times the beam length is equal, or is called the member constant for torsion. And the smaller this value, the greater the influence of the warping torsion usually is. So that's a nice parameter that can tell us already if a section or a member with some certain section and a certain length is prone to warping torsion or not. So we clearly see that the section choice impacts whether warping torsion is relevant for our calculation or not. And for that purpose, it's common to categorize the sections that are available into 3 different categories. So that I want to just quickly show you here. Sections with a warping constant of 0 are called warping-free sections. Such sections do not show any warping deformation and remain plain under torsional loading. So the following sections are perfectly warping-free: the circular hollow or circular solid section, thin-walled cross-sections whose profile center lines meet at one point, like this L profile or the T profile, quadratic hollow sections with constant thickness, or which is a rather special and academic case, but some rectangular hollow sections with specific height to width and thickness ratios. Then there is the second category, and that's the category of minor warping cross sections. So the warping stiffness of such sections is not 0, but relatively small compared to the torsional stiffness. Although a universally accepted definition of what is relatively small is not available, or at least is nowhere like fixed in some standards, it is usually acceptable in civil engineering applications to neglect warping torsion for members with an epsilon t value or member constant for torsion value greater than 10. Usually closed sections and many solid sections can be treated in such way. At the bottom, I have calculated the member constants for some sections that I have shown here. So of course, we need to assume or have a length to calculate the member constants, and I assumed just 1 meter, which is quite short for a civil engineering application member. So we see in that category that we have like rectangular hollow section, trapezoidal hollow sections. We have an I section with some reinforcement plates at the sides, then forms a multi-cell section basically. We have some hybrid sections, so there's a box section with some unrestrained parts, but still in this case the member constant would be greater than 10. And we have a solid rectangular section with a height to width ratio of 2. So for like timber or concrete design, where we have mostly such profiles or sections, we can safely say that warping does not play a major role because the member constant is quite large here. So it's rather, as I said in the introduction, rather interesting for thin-walled sections made of steel. And the category that is really affected by warping torsion is the third one, so the non-warping section category. All open and thin-walled sections that do not belong to the first category of warping-free sections are actually non-warping-free sections. These sections, they show significant warping effects under torsional loading. And as you can see, some very prominent steel sections, such as the I profile or the U profile, belong to this category. Also, cold-formed thin sections are very prone to warping, and you can see that the warping member constant, or the torsional member constant here in this case, is much lower than 1. So in some cases, it's rather recommended for such sections to neglect the primary torsion rather than the warping torsion. Yeah, but now that we have gained some theoretical background on the influence of the section shape on warping torsion, we can move over to RFEM to make our first example and see if we can back up the information that we just gained on some simple example calculations. So what have we learned until now? We have learned that we have 2 different types of bearing mechanisms for torsional loading. Some non-torsion or primary torsion and the secondary torsion, which goes along with warping torsion. And then we have an influence of the section where we have 3 different categories, and only non-warping free sections are or can be assumed to be prone to warping. And we will check that out now in RFEM. Therefore, I will now jump into the program with you. So let's just go into our model, to RFEM again. We have here an empty model, more or less. We have the sections in here, some warping free, minor warping, and non-warping free sections that we have just uncovered earlier. We have some nodal supports that I have predefined just to save some clicks. And I have a first load case that shouldn't actually have any loads. So let's just delete those loads. And the load case does not have any self-weight active, so we just want to investigate simple examples under pure torsion. So let's do so. I want to start with a very simple static system, and I want to model a cantilever beam with a non-warping free section to see if we already can catch the influence of warping here in this very simple case. So I assign a fixed support to one of the nodes, and on the other end of this cantilever beam, I apply a concentrated moment of 1 kilonewton meter. All right. And I think there's no add-on activated right now. So let's just do a blank calculation with 6 degrees of freedom to have some reference that we can come back to and compare the results with warping torsion active actually. So I just click on calculate, and what we get now are the local deformations, the internal forces, strains and stresses. But let's keep an eye on the local deformations and forces that are actually now calculated here. We can see that we have 6 of them. So these are the 6 local deformations that are usually taken into account: 3 translational and 3 rotational local deformation. And when we check those, should only have rotation about its own member axis, about the x-axis. And when we look into the internal forces, we only have a torsional moment of 1 kilonewton meter, and this is constant from one member end to the other. All right, so now actually let's add the 7th degree of freedom. Therefore, we just go to the base data of the model, go to the add-ons tab and activate the torsional warping add-on and run the simulation again. And let's see if we see any difference here. We already see in the result quantities, we have now a 7th degree of freedom, the warping degree. We can actually show this warping degree of freedom and the value it has. Actually, it's not 0. So it seems that something happened. And if we look into the internal forces, we now have still our torsional moment, which is now composed of the primary and the secondary torsional moment. And if we check how this torsional moment is now distributed between primary and secondary, we see that in this case, in the very basic case that we have modeled here, all of our torsional moment belongs to primary torsional moment. And since we said that the integral of the secondary torsional moment resembles our warping moment, of course, if the secondary torsional moment is 0, then our warping torsional moment is also 0. But why is that? We just said that an I section is non-warping free and is very prone to warping deformation and warping moments. So what happens here? Maybe that gets a bit clearer if we check the deformations here. So we see that we have this twisting of the beam, but when we look from the side, and maybe let's scale this up a bit, we can now see that there's also warping in our section. And we can actually see that the member warps at both member ends freely. So we don't have any warping restraint here, and that's why basically this cantilever can freely warp at both ends. And as long as we don't have any warping restraint, then it's just deforming in this mode. But from this warping deformation, we don't get any additional forces or stresses in the beam. So we can also check stresses. We don't have any actual stresses here. So what we need to really activate warping torsion is also to add a warping restraint. So let's see how we can do that. I copy the cantilever, add a second one, and now I just want to quickly look with you into the nodal supports. But as you can see, even after turning on the 7th degree of freedom add-on, the warping torsion add-on, we still only have 6 degrees of freedom that we can constrain here in the nodal support. And that's basically because the warping degree of freedom is highly a local one, and it only affects beams and not any like surfaces or volumes that you could also support by these nodal supports. So that's why we actually put the warping constraint into the beam properties. So we attached the warping degree of freedom to the member object. So if we go to this member, I just double-clicked on it to open the Edit Member dialog, we can now set transverse stiffeners. Those are only available when we have design add-ons that use transverse stiffeners, or if we have activated our 7th degree of freedom. And under those transverse stiffeners, we can define a new type of transverse stiffeners. And of course, we find some conventional stiffeners. That's what you basically would probably expect under this title, transverse stiffeners, some flat stiffeners, or maybe some angles or channel stiffeners. But what we also find here are warping restraints, actually. And we want to take this to now add a warping restraint at the fixation of this cantilever, so at the left side. So I just generate a transverse stiffener type with a warping restraint at x equal to 0, and I want to add a full analytical warping restraint. I could also insert a warping spring here and give some value here that I calculated based on maybe an end plate thickness or whatever. But in this case, we want to make it clear, and we want to have a full warping restraint. So I will just agree with that and again say OK. And now we see indicated here we have this thick orange plate at the end. And this actually is a warping restraint that we now added as surplus to the nodal support condition that we applied here. So let's do the calculation again. And now we should actually see a difference in the solution. Okay, and I have activated the axial stresses, and we now directly see by comparing those two that on the right side here, where now we restrained our warping, we have significant axial stresses that arise from that constraint. So we have compressional stresses at 2 edges where the member wants to elongate, and on the other 2 edges we have quite significant tensile stresses. We can also now check the share of the torsional moment. Of course, in both systems, the sum of the torsional moment along the beam is still 1. But now, on the right side, only a small portion of the torsional moment is actually sans venant torsion or primary torsion. The rest goes to secondary torsional moment. And at the restraint, basically everything goes into secondary torsional moment. And yeah, as we said before, the integral of that should be the warping by moment. So we can see in this case where we have a warping constraint at the end, we also get significant warping moments, which actually give us these axial stresses in the section. We can also compare the rotation of both members, because what this warping restraint also does, it increases the torsional or the stiffness of this member and the resistance against torsion. So we can see that at the free end of the cantilever, we now have rotations that are much smaller than in our reference system. It's more than half or less than half of the reference rotation. So that's quite interesting. That means in this case we were actually now able to activate warping in the beam. So we needed a member that is non-warping free, and we needed a warping restraint. So let's check what we have just learned about the different section types and add 2 additional cantilever beams with a warping restraint. We can keep that. But now we actually want to swap the sections for those additional members. And I want to model a section with minor warping. So for that example, I want to take an I section with additional web plates, which makes a 2-cell section out of the I section basically, but it has the I section in the core has the same dimension as our IPE 200 more or less. And then let's also add a completely warping free section. So for that I want to take a CHS section, and now we can also compare how those 3 systems with a warping restraint, just with different cross-section, react to this torsional load. So let's conduct the analysis again and compare how these different systems behave. So again, just to check for sanity, we have a torsional moment of 1 in all cases, but the secondary torsional moment already in this case where we have the minor warping section is also 1 at the restraint, but it is in the vicinity of this restraint, it very quickly vanishes. So that's actually what we expressed or what we learned about the decay factor. We said earlier that sections with minor warping have a very high decay factor, and the secondary torsional moment vanishes very quick in the vicinity of a warping restraint. And that's actually what we can see here by just comparing the member with an IPE section and with an I section and additional plates, which makes it a minor warping section. And of course, if we then again think about the warping moment as the integral of this secondary torsional moment, the warping moment is much smaller than for the non-warping free section here. And of course, this is can also be seen when looking at the actual stresses that come from the warping restraint. So let's actually focus on this member just so we are able to see something on our scale. We have minus and plus 11 megapascal, and which is just very small values compared to the 240 kilonewton megapascal in our non-warping free section here. And then go on with the warping free section. Here we actually don't see any secondary torsional moment, and of course, as a consequence of that, no warping moment and no axial stresses from this warping restraint, because this section actually doesn't warp at all. We can see that here also when we check the local deformations in the warping degree of freedom, and we can also compare the local deformations and see that our sections with minor warping or no warping, of course it's not perfectly comparable because this CHS section has a bit smaller diameter compared to the height of this section. But yeah, we can see the big differences between the rotations of this open sections, the closed sections. All right, so now we learned about not only that we have those different section categories and how they influenced the effect of warping, but we also learned about the warping restraint. So, and we have now covered in the example a warping boundary condition, so a full warping restraint at the end. However, there are additional cases or additional influences for a warping restraint. So free warping can also be hindered by changes in the torsional or warping stiffness along the member. So here are two examples for that. So for example, if we have a tapered member where the section size changes along the member, there we have a warping restraint basically. So the neighboring sections restrain each other from free warping. And the same goes, or we have also a discrete increase or change in torsional and warping stresses if we actually set or include stiffeners along the member length. So also such stiffeners can act as a warping restraint along the beam, and we will also check this in the example. But before we do so, let's check the third important type of warping restraint, and that actually comes from the loading itself. So whenever we have so far in our examples, in the 4 examples that we have already modeled, we have just applied concentrated torsional moment at the end, which means that we had a constant torsional load over the member length. But in fact, all other loading types that result in a varying torsional moment along the member also introduce a warping restraint by themselves. So all of those 3 effects or those 3 parameters influence the reaction of a member that has a non-warping free section to our torsional load. And what they have in common is that all of them lead to a situation where we have a non-constant twist over the beam length. And let's actually check this out. Let's try out how these other 2 additional types of warping affect the results. So let's go back to the model, to RFEM, and add some additional cases. So we said that we have a warping restraint when we add transverse stiffness along the member length. So we can do that also by the option by activating transverse stiffness, and then instead of a full warping restraint, we now define, for example, flat stiffeners. Let's set the first flat stiffener at 25% of the member length, and then add 2 additional stiffeners at again 25% of the total length as distance between those stiffeners. Let's increase the thickness of the flat stiffeners to 8 millimeter and assign it to this new member here. We can also check the influence of the stiffener shape, because that can also be interesting. So let's add one option where we don't use flat stiffener, but channel sections or U-sections as a stiffeners, because these form closed cells along the beam length. And I assume, or it's pretty safe to assume, that those stiffeners affect or have a higher restraint on the section. But we can check that out by just introducing them and comparing the results for those 2 cases. So I have already defined this additional type of transverse stiffeners. I just need to define or assign them to this member. So now we can see the difference of the stiffener shape. Then we said also another example for changing torsional and warping stiffness can be a tapered member. So let's add one example for that to take this into account. So we just add another cantilever with a linear section distribution type, and at the member start we will now increase the member size to an IPE 240, and at the member end, at the free end, we will keep the IPE 200. So we can see this beam is now has like a linear cross-section distribution from a small cross-section to a larger one here. Okay, and then we said another warping restraint could be induced by the type of loading. So instead of applying a concentrated torsional moment to the tip, let's actually add one example where we apply a uniform torsional moment load along the member length, which will give us a varying torsional moment over the length of the member. Okay, now actually let's run this calculation and again check how those measures or how these manipulations affect the behavior or the load bearing mechanism in torsion. So again, to check, everywhere we have a maximum torsional moment of 1 kilonewton meter. But let's actually check how much is now going into secondary torsional moment. And what we can see is that here with our transverse stiffeners, we have quite some share of the torsional moment now going into secondary torsion. And the share is much increased by introducing closed stiffeners actually. So here we have almost 70% of the torsional moment going into secondary torsion. Of course, this also leads then to higher warping by moments and in consequence to higher axial stresses coming from this restraint. Yeah. Here we can see it. Here it's the difference are probably too small to see them. We would need to focus on this beam. So we can see there's also some stresses added or introduced by this restraint, but it's not as big as for the closed cell stiffeners here. But also for the beam with a linear section distribution, we can see that we have now some warping, actual warping stresses here in the member, just because the linear, the section distribution is not constant over the member length. And also in the last case where we applied a varying torsional moment over the length, we can see that we have now warping torsion in the beam. So we have added basically a warping restraint. And as I said, all of those cases have in common that we have a non-constant twist. And we could, for example, check that by looking into the rotation along the beam and then compare the values here. I mean, it's not too obvious, but if we check, for example, the value at the end for this configuration here with a constant moment load or uniform moment load along the member length, we see that at the end we have a rotation of 88.2, and at the middle it's not half of it, but it's 84 more or less, or 84.1. So that's not actually half of 88.2, and that means that the derivation of this function cannot be constant. So the twist will not be constant here in this case. All right. So that was, I think, quite interesting and gives you some insights of when actually warping torsion is generated or under what conditions. So we need a section that is non-warping free, and we need some kind of warping restraint, which could come from the section distribution, from the loading itself, and from changing stiffnesses or warping constraints, as we have demonstrated here. To conclude with the first example, let's check how the section choice, but also the different types of warping restraint affect the resistance of such a cantilever beam to lateral torsional buckling, because that we can also investigate with our 7th degree of freedom. If we add it, we have the correct kinematics here between the torsional degree of freedom and the bending degree of freedom. And we can, it's quite simple, we just add the structure stability add-on. We just activate it. Then we probably want to generate a second load case where we don't load the cantilevers in torsion, but in bending. And now instead of this concentrated moment at the end, we just apply a load of 1 kilonewton in Z direction at the member end, like this, which will give us a maximum bending moment at the fixed point of 1 kilonewton meter. So, but we are not only interested in the static analysis result, but we wanted to check the critical bending moments, and those we can get by assigning a linear eigenvalue analysis to this load case 2 that we just generated. And I think 4 eigenvalues are not enough, so I will just increase the number of eigenvalues that it should calculate for this example here, so we can see the eigenshapes of multiple beams and investigate and compare them. And that's basically it. So we now not only get the results of the static analysis, we can quickly check how the internal forces are. Now we have no torsional moment here, we just have bending about the strong axis, and we only, and we have a maximum bending moment at the fixation or at the boundary condition of 1 kilonewton meter. But now we also get the stability analysis results, and this gives us the eigenshapes and the eigenfactors. And those eigenfactors or critical load factors are the values that we can multiply the internal forces with to get our critical load. So that would mean that for this reference case, a bending moment of 208.7 kilonewton meter at the fixation would be our critical moment. So we see this is also the member with the lowest critical moment. So if we browse through the results, we see, okay, the stiffeners, the flat stiffeners, they increase the critical moment a bit. So the resistance to lateral torsional buckling is slightly increased. Then we have the tapered beam, which is a bit higher than the beam with our U-shaped transverse stiffeners. That makes a large difference. Also here in the investigation of lateral torsional buckling, if we compare the flat stiffeners and the U-shaped stiffeners, has a huge impact. And then we actually get the lateral torsional buckling of the cantilever, where we applied this warping restraint at the end. So we can see that by doing so, our lateral torsional buckling capacity has more than doubled from 210 to 490, more or less. So that's quite interesting to also see the effect on lateral torsional buckling. And then we can browse through, we get some higher modes. Let's see if we can get one for the minor warping section here as well. Yeah, and there it is. So for this section with minor warping, yeah, of course, we get an eigenvalue for lateral torsional buckling, but the critical moment is so high, it's almost 6,000 kilonewton meter compared to the other configurations where we found the first eigenshapes around 2 to 500 kilonewton meters. Such sections are just less prone to lateral torsional buckling, as this small example here demonstrates. And then I don't think we should find an eigenmode for the warping free section. No, we don't. So this actually does not buckle at all. All right. So just as a repetition, let's jump back to the slides. Yeah, what we just did. So to check stability modes, torsional buckling, or in this case, lateral torsional buckling. As I said before we did the example, started with the example, we need to consider the warping torsional degree of freedom. Otherwise, we wouldn't get any results for this linear eigenvalue analysis. Because only with 7 degrees of freedom, the kinematics of the beams loaded in bending, axial force, and torsion are properly taken into account. And I want to show you another example where this is quite important, and it is not related to this case of torsional stability, but it's maybe a much simpler case that you and I would probably stumble over in irregular analysis. So in the second example, I want to model a single span beam with a uniform vertical and horizontal load. So let's do that. We go back to the program. I will delete most of the members here, and then we can just take this member and make it or transform it to a single span beam. I prepared the nodal supports already, so we assume a fork support non-sliding on the left side and a fork support with sliding condition on the other end of this member. And then we want to apply a uniform load in Z direction. That should be 8 kilonewton per meter in Z direction. And then also add another 1 kilonewton per meter in Y direction. So we can even we can switch off the structure stability add-on, but we can even take into consideration second order effects just to be sure that we don't miss anything. But to show you what we would capture with a regular 6 degree of freedom calculation, I just switch all those add-ons off. And maybe for reference, I copy this member twice, just so that we can compare the case of biaxial bending with the uniaxial bending cases and check how the results differ from each other. So we will now just conduct this simple simulation. I mean, the static system and also the loading conditions are quite simple and are encountered probably in many situations. You could think of purlins or rafters that are maybe rotated around their axis, or maybe a corner column that is loaded in from two sides due to wind loads. So that could be a situation where such case of double bending could occur. So let's check bending moment about the strong axis. We have in our first and the third system where we have both combined. Then the second case and the third case, they also have bending about the weak axis. But that's basically it. Of course, we have some shear forces that fit to the bending moments, and we have some very small portion of axial force due to the rotation of the beam. A portion of the shear load goes into normal force, but that's neglectable, I would say. Also, when we check the deformation shapes, we see the first system bends in Z direction, the second one in global Y direction, and the case where we have applied loads in both directions is just a superposition of this deformation. So we see we get bending about to both axes, but we actually don't see any rotation here. And that's also supported when we check into the local deformations. We don't see any rotations on all of those members here. Okay, but what happens if we now activate the 7th degree of freedom? Let's do that. I will just activate 7DOF and run the simulation again. So here, okay, we already see I just left on the local deformations about the x-axis of the member, and we can already see that there are in fact now for our member under double bending or biaxial loading, we see there are actually now rotations. And if we check the global deformations, we can actually very clearly see that now our member is also twisted towards the middle. And this is also obvious when looking into our section forces or internal forces. We now see that in the double bending case, not only My and Mz are present, where by the way, the weak axis bending moment has now increased by almost a quarter with respect to the reference configuration. Yeah, but now we actually also have a torsional moment, and because we don't have a uniform torsional load or a constant torsional load along the beam, we should also have a share in secondary torsional moment, and this would give us also some warping by moment over the member length. So we can only capture this effect of the combination between bending and torsion, and this effect of hidden torsion that's not directly applied. So we didn't apply a direct torsional load, but due to biaxial bending we get some indirect torsion, and we can only reveal it, or we're able to reveal it by analysis with 7 degrees of freedom. Of course, I also activated second order effects. These are required as well to capture those effects. And I don't want to make you nervous and say that always in the case where you have double bending, it has a critical influence on the design. I just want to raise the awareness that if you have a double bending or biaxial bending, there's probably, at least if you are working with non-warping free sections, there is some indirect torsion that is generated by this loading condition. Actually, this is true for all cases where you have different moments or two different moments. So for example, we can check the same case but just apply bending about the strong axis together with the torsional moment along the beam axis. So let's add in a second case bending about the strong axis and torsional moment. And we should see in this case, with 7 degrees of freedom and second order effects, we should get our third moment component. So we have bending about the strong axis, bending or a torsional moment here, and then in the combination of those two, we have only also a significant portion of bending about the weak axis that is now generated here, when we consider 7 degrees of freedom and second order effects. So this is good to know that just keep in mind if you're working with non-warping free sections and you have 2 moment components, then it might be reasonable to check for the third moment component by switching on warping, torsion, degree of freedom, and second order effects, and see how large the influence is. All right, so the remainder of the time, so this leaves us with 2 examples done. The remaining time I would like to focus on some additional peculiarities that need to be considered when setting up a 7 degrees of freedom calculation in RFEM and RSTAB. So along the way, or until here, we have learned how to activate the 7th degree of freedom, how to apply boundary conditions and stiffness or discrete warping restraints along a member length, and also how to assess the results for warping torsion. So far, in our examples, we have only used sections that are double symmetric, and this means that the shear center in this case aligns with the center of gravity. So if we check the properties of this I section here on the right side, we get this nice figure, and we can also activate the visibility of the shear center. Shear center and center of gravity are coinciding, and this is of course not always the case. So for example, if we have a U profile, we have quite some difference position of the shear center and the center of gravity. For this example, there are almost 40 millimeters distance between those 2 points. So let's check what happens if we are dealing with a section that has that is not double symmetric but has a different position of the shear center with reference to the center of gravity. Let's start again with the 6 degrees of freedom analysis. So I will switch off the 7th degree of freedom. We will start with a regular analysis. I will also cut out the second order effects just to make it a bit more clear what effects we are looking at, and run this simulation again. So now we have this U section here, single span beam with the load in Z direction. And if we do this analysis with 6 degrees of freedom, we only get a bending moment about the strong axis, which is maybe what you would expect, and which is, I would say, the same in other beam analysis software, that by convention for such a system we would only get bending about the strong axis. And this is because transversal loads are usually by default, maybe you have never thought of this, are applied in the shear center. So there's no eccentricity or no lever arm of the vertical load in this case to the shear center. However, if we now activate the warping torsion add-on, this default behavior changes, and with our 7 degrees of freedom simulation activated, all loads are applied to the center of gravity. And this now leaves us not only with a bending moment about the strong axis, but also generates torsion, a torsional moment now. And of course, here we don't have a constant torsional load. Also, what we get is secondary torsional moment and a warping B moment. And if we think about the last case, if we would consider a second order theory or nonlinear geometric solution or solver, then My and Mt together would also give us some component of bending about the weak axis. But since we have now neglected second order effects, we don't get that actually, but that would be the full set of results. So by just applying a vertical load with default settings, we would get all moment components basically. Of course, we can change the default behavior by applying an eccentricity. So we could say here we want to apply this force to the shear center, and then we wouldn't have a torsional moment, and we could do it the same way in a 6D OF analysis. It's just important to keep in mind the default settings are different, and if you activate a 7 degrees of freedom simulation, you should think about these eccentricities and if they make sense or not. But this, of course, largely depends on the load application and how you would do that in the real structure. Another thing is that not only the loads are applied to the center of gravity when we turn on the 7th degree of freedom, but also the boundary conditions now all act in the center of gravity. In the normal case, in the 6 degrees of freedom analysis, we actually have the support in the transversal beam direction also set into the shear center. So that's why in the case with 6 degrees of freedom, we don't get any torsional moment and we don't get any torsional reaction load here, torsional moment and at the reaction at the support. In this case, with 7 degrees of freedom, we get a torsional moment in the beam because this load has some lever arm to the shear center. So due to these eccentricities, we have actually a torsional moment in the beam, but we still don't have any reaction moment. That here in this case it would be my, so rotation about the global y-axis or torsional moment about the y-axis, because with respect to where this nodal support is sitting, it's also sitting in the center of gravity of this section. It has no lever arm. So in this case, and that can confuse people sometimes, the internal force at the member end is not equal to the reaction force, but you have to take into consideration also the vertical force here of 16 kilonewton meter times the distance again between shear center and center of gravity, and that would then amount or have the same magnitude of this torsional moment in the member. So it's better to think of it to not get confused. In this simple case, we have applied the load in the center of gravity, and thus it has now no lever arm to the nodal support because it's also sitting in the center of gravity. In the case we perform a 7 degree of freedom analysis. All right, so with this being said, let's move on to the last topic, because what we have now also not considered until now is how are multiple beams or members coupled to each other. How is the warping degree of freedom transferred from one member to the other, and how can I influence the default behavior? So let's dive into this. Let's again make this an I section because we want to keep it simple and clear what we are doing here. So we again change back to our double symmetric section, and we apply a constant moment load of 1 kilonewton meter per meter. And how does it actually look when we perform this analysis? We have 7 degrees of freedom turned on, first order theory simulation, and what we get should be a torsional moment, and we should have both effects, primary and secondary torsional moment here, because we don't have a constant torsional moment. Let's disable the support reactions, not to confuse us. And of course, we should have also a warping V moment. So what happens actually if we take this member and split it, let's say, 3 times. So let's, or 4 times. Let's introduce 3 intermediate nodes, which results in 4 members now that are equally loaded as before, but we just have an additional node here. And the default behavior for all other degrees of freedom is that when I connect members at a common node, then all forces are transferred. So all bending moments are transferred from left to right. Axial force and shear forces are all transferred from one member to the other, as long as I don't have defined any member hinges. However, for warping, this is slightly different, because what we assume for the warping degree of freedom is that at member ends we have a warping hinge by default. So when we compare the results here, we see that in the intersections between those two members at the intermediate nodes, our warping moment approaches 0. So this is basically a warping hinge introduced every time we split a beam. And that's the reason for this is because it's often times, or I would say in as many cases as we would assume that there is a warping continuity between two beams or two members, as between this and this member, I would assume that the warping degree of freedom is continuous, in fact, because warping is transferred mainly in this case by the flanges, and the flanges are continuous. But there are equally many cases where this is actually not true. So if we have a member that maybe connects from the side here, that is maybe connecting in this point. In this situation, it wouldn't be so clear anymore how the warping degree of freedom, which is transferred again by the flanges, is transferred to the member that runs into the other direction. Or same could be true for a column that we place here. Where it also would not be trivial to define how the warping degree of freedom should be transferred between one member and the other. So thus the basic behavior, or we decided that in our software, the basic behavior is that we uncouple the warping degree of freedom between adjacent members. But what we can do, if we want to couple them, is to generate a member set, to group them up in a member set of the type continuous member. And if we do so, we see now that this is indicated by these dashed lines here, and we run the simulation again. This third configuration should give us the same results as the first one. And we can actually see that now at the intermediate nodes, we still have some warping moment that is transferred from one to the other member, and we get the same results actually. So be careful whenever you work with 7 degrees of freedom. The default behavior is that the warping degree of freedom is not coupled from one member to the other. And there are also some, as I just said, it's not very trivial in many cases how the warping degree of freedom is transferred. And we can couple them via this member set by grouping them up. But what actually happens if we have some discontinuity in this beam? For example, what happens if we have, let's say, we have a different section here in the middle of this member set. We have an IPE 240 here instead of the IPE 200. And now, if we think about how the warping degree of freedom is transferred for this I section, we said it's transferred through the flanges. Then there would be some gap here, yeah. At least in our simplified beam model, there would be this gap, and it wouldn't be clear how should the program treat this. And in this case, even if we coupled them in a member set, it would give us a plausibility check warning saying that the topology of the member or the orientation is not compatible, and continuous warping cannot be assumed or cannot always be assumed. That's how you should read it. And I can still ignore it. So by pressing ignore, it will still assume continuous warping here. But it's just giving you a hint that there is some discontinuity and you have to look into this. But because many times the actual way the warping degree of freedom is coupled depends on constructive details. So for example, how do you how does your detail in a member to beam connection look like? This very much influences the coupling conditions for warping torsion, and we can also check this here in this example. So if we are in doubt or have no idea how the warping actually should be coupled, and we want to investigate it further, so in many times it's just engineering judgment, and probably here when you do something like this, this beam would probably also be loaded in bending, so you would definitely put an end plate here, or you would elongate the flanges of the smaller section into the larger one. But if you want to see the influence of such constructional details, what you could do in RFEM, and you could do that quite easily, would be to make a surface model of this member. This is also easily possible by just generating surfaces from these members, and then you would have a nice set of surfaces where you could start your surface analysis from. But due to the time limitations, I would now jump over to a model that I have already prepared, where I have basically done all the work already, where I have changed or applied proper boundary conditions, where I have applied a proper mesh, where I have changed the torsional load to a pair of line loads to the surface. So we can see here this would be my surface model. And now I have created two situations. One where I just left the surface model as it was when I generated it from these members here, where I basically have a gap between the flanges. As I said, nobody would build that in that way, and it doesn't make any sense because also bending continuity would be a problem here in this case. But then I have the second option here as well, where I just elongated the flanges of the smaller section into the larger one. And then as an additional step, I have defined some result beams on top of this surface model. And what this result beam does is it integrates all the stresses from the surfaces and gives us internal forces. And this also works in combination with the 7th degree of freedom. So we will also get the warping by moment when we use these result beams. And this means we can now just run the simulation. Okay, it gives us the warning because we have some configuration where we have different sections in one member set. But we now can very conveniently compare. Let's switch off the surface results and the loads maybe to have a better overview of the situation. We can now very well compare the warping moments for those configurations. So here we have the beam model with continuous warping. So it's minus 0.6 kilonewton per square meter in the beam model case. Then in the first surface model case, where we don't have any connection between the flanges, we actually see that the warping moment in the connection between those two members is actually close to zero in the result beam. So when we integrate all the axial stresses about the shear center here, we don't get any warping moment whatsoever. And then the third configuration, where we have elongated the flanges of the smaller section into the larger section, we actually can see that here we have pretty much continuous warping. We, in this case, even have a slightly higher warping moment at the middle, because we here have a section that is has a much higher torsional stiffness that has 4 flanges. So these are taken into consideration also in this shell representation here. But yeah, that of course, as I said before, this is just a stupid idea to do this connection like we assumed it here in this shell modeling approach. But it shows that the constructional details very much influence what assumption is correct for the coupling of the warping degree of freedom. I mean, the same goes for connections between beams and bending and shear and so on. Of course, the constructional details need to fit with the modeling assumptions. But yeah, all right. So I think this was also quite interesting, and yeah, I would like to. The most important thing from this example is, if you switch on 7 degrees of freedom, make sure you have your coupling conditions between the members right. So you have to, so you have continuous warping wherever you want by applying these, or by grouping members into member sets. And I think with this being said, I would like to close this webinar, at least from my side. I think it's enough input for your convenience and to have a better overview of what we have talked about. I prepared this little summary where I basically put all the important things that you need to consider when switching from 6 degrees of freedom to 7 degrees of freedom. And you can treat it like a little cheat sheet that you can print out or open when you do such analysis, and check for the most important things that I've summarized here. All right, and then yeah, one last gift, so to say, I have for you, yeah, would be some further reading recommendations. I have assembled some media recommendations here on this slide, and yeah, the content of these sources are sorted by complexity. So from quite simple educational and very easily understandable to complex and very detailed. There's something for every one of you, I think. Yeah, and with this being said, I would like to thank you for your attention and the participation in this webinar, and hand over to Andreas again for some final and concluding words. All right, enjoy the day.
Thank you, Jonas, for your nice presentation. I have gotten an additional hint. Our new online courses are on our website. Courses to RFEM 6, Eurocode 2, reinforcement, reinforced concrete design. Then the Eurocode 3 course for the steel design. For more information, you can press the buttons here for with the links. Also, you can scan the QR codes. Yeah, the courses takes between 2 and 3 hours. You can interrupt or stop the course anytime and continue when you have time again. The courses consists of several parts. Okay, that should be also all from my side. I thank you for your attention. Thanks to Jonas for the presentation. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.